series. Tonight, I'm very excited to welcome Dr. Jonathan Allan. We have a really great presentation for you tonight, and first, I will start with a few introductions. So my name is Kaya Hazard. I'm the Oregon Regional Manager for the Surfrider Foundation. Surfrider is a nonprofit group working in coastal states nationwide, and we work on many different initiatives to protect our ocean and coastline. In Oregon, these range from monitoring water quality, protecting special places like marine reserves, fighting against plastic pollution through beach cleanups and progressive policy, and making sure that Oregon's beaches remain public and accessible. To that end, Surfrider has teamed up with Oregon Shores to launch our new campaign, Oregon Beaches Forever. As many of you know, Oregon's beaches are threatened by the coastal squeeze between coastal development and the armoring built to protect it on one side, and on the other by sea level rise, climate change, and more intense storms each winter. So through this new campaign, we'll be taking a more holistic approach to protecting our beaches. We will continue to oppose shoreline armoring along our coast as it is harmful to our public beaches, but we will also be advocating at the local level for climate adaptation and improved shoreline management, such as through the current update to the Clatsop Comprehensive Plan. We will be working to implement nature-based solution model projects and policies that promote beach preservation and climate adaptation. And we are also excited to be working with both Oregon State Parks and DLCD, the agencies that manage the shoreline, on their rulemaking processes to update and improve existing regulations for shoreline armoring permitting and access to and along the shoreline. So if you would like to learn more about this campaign and stay up to date with upcoming educational events like this one, you can find more information on both the Surfrider or Oregon Shores websites, and I will drop those links in the chat. We have one more webinar in this series to finish out the year. That will be coming up on December 4th and will feature Professor Peter Ruggiero, and I will drop that registration link in the chat as well. And if you just can't get enough, we will also be at State of the Coast this weekend, presenting on a panel on Oregon's beaches on Saturday afternoon. So with that, I will pass it over to my colleague, Jessie at Oregon Shores.
Thank you, Kaya. It's really nice to be here with Surfrider and with Rhiannon and Jonathan. My name is Jessie Jones, and I am the Coast Watch Programs Manager for Oregon Shores Conservation Coalition. For more than 50 years, Oregon Shores has served as the state's leading voice when it comes to protecting the beaches, headlands, landscapes, and ecosystems that make Oregon's coast so spectacular and loved. We have a mission to engage, educate, empower people to protect and increase the resilience of the coast's ecosystems, landscapes, and communities. And we are a proud partner of Surfrider in many ways. As I said, I am the current programs coordinator, programs manager for Coast Watch. Coast Watch engages people in documenting Oregon's sandy beaches and rocky shores for natural and human-caused changes, wildlife, and phenomena. Volunteers are linked to a section of the Oregon coast to observe seasonally. The program offers education about shoreline ecology, natural history, and opportunities to contribute data to community science. And so if you have any questions or you want to contact me about adopting a mile of the beach and community science, I will put my email in the chat. And at this point, I would love to hand it over to Rhiannon, who is a partner on one of our community science projects, the Oregon King Tides Project. So Rhiannon.
Thanks, Jessie. I'm Rhiannon Bazor. I'm the Coastal Shores Specialist with the Oregon Coastal Management Program, which is administered by the Oregon Department of Land Conservation and Development. And I, along with Jessie, am the coordinator of the Oregon King Tides Project, which is currently in its 14th season, 14th year. We just saw the first set of King Tides for the season last weekend in November. The next set will be December 13th to the 15th. And we ask that community participants, visitors to the coast, residents of the coast, anybody who's interested in viewing these really exciting king tides and the impacts that they have on our coastal communities, including erosion and flooding, take photos of the king tides, and from a very safe distance, of course, and submit them to our account, which is at www.oregonkingtides.net. And it will walk you through a very easy submission process so that you can help document the effects of these king tides, and we can see what sea level rise may look like in the future for our communities, so that we can help our communities start to plan for these future conditions. And thank you, Jesse, for putting those in the chat, so you can visit that website. And now it is my honor to introduce Dr. Jonathan Allan. Dr. Allan is a coastal geomorphologist with the Oregon Department of Geology and Mineral Industries. He completed his PhD at the University of Canterbury in New Zealand, and then went on to complete a postdoc at OSU in the College of Earth and Atmospheric Sciences, working on the effects of extreme storms on Oregon beaches. Then in January 2001, he joined DOGAMI and has undertaken research on a variety of topics, including coastal change mapping, coastal flooding, and the effects of tsunami. He also established the Oregon Beach Shoreline Mapping and Analysis Program, and he currently leads the tsunami modeling and mapping program for the state of Oregon. So with that, I will pass it over to you, Jonathan.
Thank you. And thank you, everyone. I appreciate the opportunity to come along tonight and just talk a little bit about coastal geology. Obviously, it's a topic of great interest to all of us, and I guess, you know, the recent discussions and hoopla over the bomb cyclone that was developing or had developed offshore our coastline just 24 hours ago really is a testament to the concerns of these types of extreme storms and their potential for impacts. And it really is a reminder about some of the challenges we face along our coastline. So I'm going to be talking broadly about Oregon coast geomorphology. In particular, I'm going to emphasize the role of a variety of different processes, waves, tides, and the role of the El Nino Southern Oscillation in terms of affecting coastal processes, and how the compounding effects of these processes leading to the changes that we're seeing along our coastline today, and what we might expect to see in the future. Because certainly what we see today is really an analog for the types of problems that we are likely to experience in the future. And so I think some of these issues are obviously highlighted perfectly in this image here, showing the effects of extreme storm wave run-up in Nisquin in 2008, resulting in overtopping and eventually undermining the foundations of a series of homes there. And I'll actually show a little video of this area later on in my presentation. And then on the right is you know, again the relationship between placing buildings close to the coast and the hazards that they generate, and then obviously the long-term changes that are happening in other parts of the coast, like up on the Clatsop Spit, as highlighted in that upper image there. So a little bit of background for those of you who are not familiar with the Oregon Department of Geology. So the Oregon Department of Geology is comprised of two programs, the Geologic Survey and Services, of which I'm part of, and then the Mine Land Regulation and Reclamation Program, which is our program 2. So within the GS&S, there are really 6 thematic areas focused on earthquake hazards, mapping landslides, mapping flood and channel migration, the coastal program, which deals with tsunami and coastal erosion. And then underpinning all that is basic geologic mapping, identifying the geologic units, and then mineral resource evaluation. And then actually underpinning both programs is the LiDAR mapping program, which really came about in around 2008, 2009, and has grown significantly over the years and has produced some of the phenomenal data sets that we work with for doing geologic mapping, but also for developing, you know, future forecasts, for doing tsunami modeling and things like that. So I'm obviously just going to talk about the coastal portion of it. So the Newport Field Office, it's based obviously here in Newport on the Central Oregon coast. It was established around 2000. And the goal of the field office was really stemmed from a series of extreme storms that actually impacted the Oregon coast in the late 1990s, specifically the 1997-98 El Nino, and then the more extreme 1998-99 winter season, when we experienced a series of unprecedented storms, resulting in very extensive erosion along our coastline. And so the field office was really set up with the goal of assisting coastal communities with land use type decisions, with the goal of building personal safety by helping them understand processes and hazards that ultimately are shaping our coastline. And so within the field office, we have, again, two core areas of focus, one relating to tsunami hazards. And I'm not going to say too much about it, other than the sort of last couple of slides at the end of my presentation. But I'm sure, as a lot of you are well aware, we are exposed to significant risk from a great earthquake happening on the Cascadia subduction zone. And over the last 3 decades, our program has developed the tsunami inundation maps and evacuation maps for the entire coast. We've done evacuation modeling, and we've developed tools that can assist the public at large, but also planners prepare for this pending disaster. On the right, which is really going to be the bulk of the focus of my presentation, here we're focused on coastal change and understanding the impacts of storms, as well as future climate change and how that might result in increased hazard and risk to our communities up and down the coast. Within that program, we've really been doing a lot of work focused initially on developing erosion hazard maps. We've done this for almost half of the Oregon, well, actually half the Oregon coast. We've done landslide studies. We, in between 2010 and 2015, we updated all the coastal flood modeling for FEMA. Prior to that, the flood maps had been based on modeling and mapping that was done in the 1970s. So the work that we did represented a very significant update on that, based on a lot of new science. We've been doing a lot of work focused on assessing soft engineering, particularly dynamic revetments, so cobbled beaches. And then in particular, one of the things that I discovered when I first joined the agency and moved to the Northwest in general was really the dearth of information about what's happening on our beaches and bluffs. And so a major goal of mine has been to establish a dedicated observation program where we can actively monitor and document changes happening at both seasonal, interannual, and now merging into multi-decadal type observation. And these data are all fundamental for doing erosion hazard mapping and flood mapping and things like that. So I'm going to start with a little bit of background information about the Oregon coast, just to give you a little bit of the lay of the land. And so this is really focused on general sort of geomorphology. So the Oregon coast, as we all know, is about 360 miles in length. But the Pacific Northwest in general is really made up of 4 sort of predominant coastal geomorphic features. And so if we begin in the far north, up in the Olympic Peninsula, we've got an area that's dominated by rocky shorelines. And those rocky shorelines also extend throughout the central coast, and you can find them down on the south coast as well. We have duneback beaches that really comprise the bulk of the coastline of Tillamook County, Clatsop, and then up into southwest Washington, along Long Beach Peninsula, the Grayland Plains, all the way up to Point Grenville. And we also have significant duneback beaches down, obviously, in the Coos County region, particularly along the North Coos Spit. We also have significant coastline that's what we call bluffback or cliffback beaches, and they make up really all those little red dashes that you see in this map here, areas that are bluffback. And they really are concentrated on the central Oregon coast, with a few areas up in the Cannon Beach area, and then of course further south on the south coast. And then the last sort of geomorphic group are the plunging cliffs that really characterize all of the south coast, from about Port Orford southward, and then obviously the Olympic Peninsula area on the north coast. So we can do some basic math with all these different types of units, and it turns out that Duneback beaches and bluffback beaches make up roughly a third of the coastline, each respectively. The rocky shores make up about 25%, and then the other is things like mixed sand and gravel beaches, cobble beaches, and so on, that comprise a very small portion of our coastline. So within these areas, there, in what I've highlighted here in red, areas that are dominated with people. And not surprisingly, wherever we have people, we also have hazards, especially as you can see in the image on the Bluffback Beach image there, where you've got a house perched rather precariously right at the edge of the cliff there. And we have a lot of examples of that, particularly in the Central Coast area. But we also have similar problems experienced elsewhere up in Tillamook County and even Clatsop County. So these are obviously the areas where there's a lot of hazard that's ongoing, and where we're likely to experience future problems due to climate change and sea level rise. And then, of course, there are other areas of concern, like down by Coos Bay, with significant erosion happening on the North Spit. And then actually some of the highest erosion rates on the Oregon coast can be found down by Nasika Beach, near Gold Beach there. And that's primarily because of the local geology is a very soft barrage of rock that's easily erodible and is carving away as cliffs and resulting in very rapid rates of erosion. So I'm going to step back in time a little bit, going back 18,000 years. And so the image on the left there shows sea level from 10,000 years. So if you look at the x-axis, 10,000 years all the way up to around 23,000 years. So at the peak of the last glaciation, about 18,000 years ago, sea level was somewhere on the order of about 120 meters lower than what it is today. So about 400 feet. And if you look at the map on the right, that 400-foot contour line equates to roughly that black dash line. So that's approximately where the coastline was 18,000 years ago. So from 18,000 years ago to about 10,000 years ago, sea level rose rapidly up along and crossed over the continental shelf. So in the space of about 8,000 years, sea level rose almost 80 meters. And by around 8,000 years ago, would probably be located close to that magenta line or pink line on the map there. So very, very close to the coast. So between, say, about 10,000 years and 8,000 years ago, sand would have actually been migrating freely up and down along the continental shelf there. And then as sea level progressively got closer and began to interact with our coastal geology, and specifically our resistant headlands and features like that, then that sand started to move in to form the barrier beaches and spits that we see today, and the headland bounded stretches of coast that we experience today. So the sea level curve in the middle foreground of the image here is some work that was done by Tina Jura and her colleagues. And so we can see that at around 4,000 years ago, sea level was about 15 feet lower than what it is today. And by 2,000 years ago, around 8 feet. So really our coastline today, what you see is in terms of our coastline today, is really the product of the last 4,000 or 5,000 years. So it's a very young phenomenon, so to speak. So we can actually delve into the characteristics of the local geology and try to put some dates on the features we're seeing out here. So the image on the left is a view at the top there looking south along the Clatsop Plains toward Tillamook Head, which is kind of covered by my Duneback Beaches label. And on the left-hand side of the image is a series of marine terraces. And then to the right of that is a progradational or aggradational sequence of sand that is accumulated over a period of time to the present-day coastline that you can see there. And you can see in solid dark green is a line of shore pine and buildings, and then all the area seaward of that is European beach grass that has stabilized those dunes there. So we look at the geomorphic map that's below that. We can see on the right of that map there, the marine terraces in gray, captured by airborne LiDAR. And then what we've been doing is actually mapping the features of foredunes and wetland areas and interdunal areas across the Clatsop Plains. And we've been doing this all along Tillamook County, Clatsop County, and Lane and Douglas County. And the goal is to obviously develop these updated maps for the entire Oregon coast eventually. So we're fortunate in that there's been quite a bit of work that's been done by researchers at Portland State University, particularly Kurt Peterson and his students, and they've been doing a lot of dating work in early 2000 to about 2010. And so we can overlay those dates on a map like this and begin to see, you know, ages of when features were developed. And so it turns out on the Clatsop Plains, the back edge close to the base of the marine terraces there have an age of around 4,000 to 5,000 years. And then as you progress seaward, so westward from those terraces, we see younger and younger deposits, 2.6 to 3,000 years with this first foredune liniment here, and then around mid-Clatsop Plains, ages of around 1,000 to 1,300 years, and then all the way up to the contemporary coastline. Actually, it's an 1870s shoreline, so pre-jetty construction that's in that sort of pink dash line, with an age on the back foredune there of about 140 years. And then the modern shoreline, of course. So this tells us that at least in this part of the world, the coastline is very young. On the central coast, we also have, where we have, you know, dominant bluffback beaches, we have a different sort of geologic, geomorphic character about the coastline. There we have a series of shore platforms with uplifted marine terraces, such as shown in picture 1 here. And these marine terraces extend several hundred feet above the present day sea level and have ages on the order of 80,000 years, which is the lower terrace up here, all the way up to a few 100,000 years for the highest terraces up on top of Cape Foulweather. But it's the shore platform, the contemporary marine terrace that's evolving at present day sea level that's of interest. And based on some work that Roger Hart and Kurt Peterson had done, they were able to identify all these exposed tree trunks. These were in situ out on the beach there. They were being exposed as a result of coastal erosion. So the example of the image here is from Nesquin, the ghost forest that you see up there. And it turned out, you know, these forests had basically evolved out onto the platform over the last several thousand years, and then were inundated with sand, and eventually the trees died. The ocean sea level approached present day levels and started to erode into our coastline and exposing the root wads of these trees there. So using these trees, Roger and Kurt were able to go out there and carbon date the tree trunks, and they found that these trees were on the order of a couple of hundred years old, so about 200 years old, based on counting the annual ring growths in the trees. But when they dated them, you can see ages on the order of anywhere from the youngest up in the Netarts area of around 1,000 years to as much as 4,000 years in the Beverly Beach area. And of course, you know, we're starting to see a lot of these in situ tree wads now being removed and eroded away and disappearing. But that tells us again, you know, something about the evolution of our coastline. It's very young. And then, of course, there's a complicating factor that I alluded to earlier in regards to Cascadia, in that we have these periodic great earthquakes that happen on the order of anywhere, well, on average about 500 years, but the range is a few hundred years either side of that. And along our coastline, when one of these events takes place, the shoreline is co-seismically lowered by on the order of 3 to 6 feet, depending on where you are on the coast. And so these co-seismic responses, and the example that I'm showing here is from Brian Atwater's work, is an example of 7 earthquakes going back almost 4,000 years. And you can see the relative frequency there, and how the coast is lowered and then abruptly starts to return, and as tectonic uplift starts to build and strain builds on the subduction zone again, until it reaches a point where marshes start to develop and eventually trees and forests can actually form out there. So this process obviously complicates this evolution quite a bit, and it's an area of ongoing research. So if we go and look, if we come up to present day conditions and we look at our coastline today, So our coastline is characterized by a series of 18 or so littoral cells. And each of these littoral cells refer to headland-bounded stretches of coast in which sediment is moving in constant flux in response to the effects of storms, of changes in ocean water levels, in response to sediment inputs, and as well as sediment losses. And this is a fundamental aspect about the work that we do in terms of understanding whether a coastline is predominantly eroding or predominantly accreting or is doing something else. And within this beach sediment budget, we can identify various inputs of sand coming from terrigenous sources. So basically upland areas that are eroded down, and those sediments are carried into our estuaries and then eventually makes their way out onto the coast. We can lose sand in extreme storms where those sediment may be taken offshore into deeper water, and it becomes much harder for that sand to come back onto the beaches. And then, of course, we have eroding cliffs bringing sand in, and sand moving in flux due to longshore currents, which is a function of variations in wave approach angles and things like that. And of course, we also have losses that occur where sand is carried inland to form dunes, like on Nitat Spit here, and are removed for a period of time until erosion catches up to them. So this is kind of a key fundamental aspect about a lot of the work that we're interested in. So when you look at the sediment in those beaches, it turns out that they have some interesting sources. And so the same image on the left there showing the shoreline at around 18,000 years ago, the shoreline at around 8,000 years ago, and the contemporary shoreline. And then in the middle here is an assessment that was done by Paul Comer and a student looking at the presence of heavy minerals out on the beaches. An example of the heavy minerals is the image on the right there, where we've got this beautiful shades of white to green to pink to black. And you can find these when you walk out on the beach there at low tide, particularly in mid to late winter, you can see beautiful examples of this up and down the coastline. And these minerals gives us clues about the provenance of where these sediments were coming from. And so, for example, the pink that you see in the image here, it turns out that there are much higher concentrations of pink, which is garnet, on the south coast, and that concentration decreases northwards all the way up to Tillamook Head, where it then peters out. And it turns out that these garnets are actually sourced locally from the Klamath Mountains in Northern California and Southern Oregon. And so the fact that they're actually on our beaches today, up here on the Central Coast or even on the North Coast, is a testament to the time when sand was actually being transported around a few thousand years ago, where the effects of these headlands were nominal at that stage. And so these garnets were actually being distributed along the coastline. And we can see similar patterns with hypersthene, also decreasing northward until you get north of Tillamook Head, where we get large influxes of hypersthene and hornblende, which are being carried down by the Columbia River and being trapped on the Clatsop Plains there. And then other places like central Lincoln County, all the way up into Tillamook County, we see abundant augite, which is locally sourced from the Coast Range, a product of erosion and downweathering of those areas. And so these sediments tell us a little bit more about the history of the coast. But of course, the most abundant sediment on our beaches today are really the quartz and feldspar that are characterized by the white and browns that you see today on the beaches. So switching gears now, we're going to talk a little bit about geohazards on the coast. So there's, and I'm sure everyone is well aware of this, we're exposed to a variety of different types of geologic hazards when we build adjacent to a dynamic coastline like the Pacific Northwest coast. So the image on the upper left there is from Pacific City in 2011, and you can see homes built on the foredune there, but you can also see sand influxing around those homes. So I mean that's an issue, and a well-known issue that's been a problem for this particular area for some time. Sand has even accumulated to such an extent that it's buried homes, it's caused building roofs to collapse and so on. So it's really an indication that there are certainly areas that we should not be building our properties on, such as these areas. We also are well aware of the impacts of extreme storms. So this is Cape Lookout State Park, in 1999. If you were visiting this park almost 20 years before this photo was taken, you would have seen a very different picture. This exact same site would have been fronted by a massive foredune on the order of about 30 to 40 feet high and extending well seaward out to about where that surf line is. And obviously, in that 20 years since, we've seen very dramatic erosion at this particular site. We also experienced extreme flood events. This is Nisquin in 1999, just behind or by Hawk Creek there, and Nisquin Creek coming in from Cascade Head to the right there. And this is a condo complex, and what's neat about this is that, you know, we have elevations from LiDAR, ground elevation there, which is about 5.5 meters or about 16, 17 feet elevation. The first floor ground elevation of the units there is probably on the order of about 22 to 25 feet. And what you can see is a combination of high tides combined with run-up from storms and storm surge, effectively inundating the ground floor of these homes here. So obviously a bit of a problem. In places like Beverly Beach on the Central Coast, another area, but these are bluffback areas now where we've got ongoing erosion, and this is testament based on these horizontal drainage pipes that are inserted at the Carmel Knoll landslide. These drains were inserted in early 2000, and this is a photo taken in 2016. So we can use data like this to get a measure of the degree of erosion that's going on at this particular site. And we know, of course, that it's happening gradually, but it's ongoing. We can also experience very rapid bluff erosion taking place. So this is an example of Glen Eden Beach in 2006. And 24 hours later, this is what the same site looked like. They essentially lost their entire backyard as a result of the formation of a rip embayment that developed at the toe there, causing localized erosion, as well as other processes from piping effects that destabilize the bluff face. And then lastly, we're obviously influenced by landslides that can also affect our highways and properties along our coast. So this is the Three Capes Highway in 1999, which then again failed earlier this year in January in a similar fashion. So what I'm going to show you now is a video of a major storm hitting Nisquin in 1999. This is the March 2nd to 4th, 1999 storm. And you're going to see some viewpoints from 3 different locations, starting at the bridge, located here with the elevation 5 meters, a view closer looking towards the condos down behind Proposal Rock there, and then another one out on the open coast near another condo. And so hopefully you can see all this. And so you can see the effects of a very high tide, coupled with storm surge and wave run up superimposed on top, rushing in up Hawk Creek. You can get a sense of the amount of water and velocity, and all this area was flooded, including a lot of property up the creek there. So this is a view looking back towards the same bridge, and you've got a couple of people standing on the bridge there. You can see the water piling up. And obviously not a very good place to be. And now we're out on the open coast by the Pacific Sands Resort, when they had quite an extensive area of grass in front of them, and showing the degree of erosion taking place at that site. You can see the effects of what we call a collision storm or collision event, where waves are impacting against the sandy dunes there, eroding into the dunes. And we're now starting to see end effects happening to the side, where it's preferentially eroding against the riprap structure. This is on the north side of the Pacific Sands, again showing the effects of that compound flooding that's going on, with foundations starting to be exposed. And then the next shot is 24 hours later, after the peak of the storm, and you can see the effects of damage to the property, damage to the riprap that was being put in at the time. and how it's all slowly being undermined. And so, based on that, we can really begin to see that our coastline is affected by a suite of processes. And not surprisingly, these range from things like large storm waves, changes in ocean water levels, particularly as a result of El Niños and storm surges. We also experience a longshore movement of beach sediment that can also result in hotspot type erosion like we've seen in places like Nisquin. We can also have the effects of rip currents, and then of course sea level rise due to glacial melting relative to land level changes. And in blue, I've highlighted those processes that are really most sensitive to climate change effects, and not surprisingly, sea level rise and variations in magnitude and frequency of storms rise to the top of the heap. But then there are other processes that tend to be enhanced during the El Nino Southern Oscillation effect, which has been demonstrated to have quite a profound effect in terms of coastal erosion hazards along the Oregon coast and up in Southwest Washington as well. So if we delve into some specifics a little bit more, so our wave climate varies seasonally, as we are all probably well aware. So our lowest wave heights occur in midsummer around July, August. So this plot here shows wave height as measured offshore from Newport, meters on the left, feet on the right there, and then monthly values on the bottom x-axis. The dark blue is the seasonal cycle, and then the red is essentially 2 sigma variation from the mean. And so that's telling us that, basically around 95% of the waves are less than 20 feet. And then obviously we're getting extreme waves reaching as much as 40 to 45 feet during the most intense events. And a case in point, the storm that we just experienced 24 hours ago was producing wave heights on the order of about 35 feet offshore from the Clatsop Plains and Southwest Washington coastline, and likely is contributed or had contributed to probably erosion problems up there. So the next step to think about is impacts from variations in wave approach angles. And so this is a conceptual model developed by Paul Komar, showing what happens in a typical year on the far left, where in summer waves arrive out of the northwest that tends to drive sediment southward. And then in winter months, the reverse happens with our winter waves being dominant out of the southwest, driving sediment back to the north. And so the whole notion behind this is over many years, the net sediment transport tends to balance out. Well, it turns out that it's a little more complicated than that. And we began to see and understand these sort of complications in the 1982-83 El Nino, the 1997-98 El Nino, and then more recently in 2015-2016. And what we tend to see is that during an El Nino year, our wave heights and wave intensity increases quite significantly above a normal year. We also see larger storm waves coming from a much more southerly direction, as highlighted in the rose plot on the far right here. So what you can see in that for the winter conditions is very large waves in the sort of 10 to 13 meter range. So in the order of 30 to 45 feet, coming from a very more of a south-southwesterly direction, whereas our predominant winter waves are from a westerly direction. And so that tends to result in more concentrated of erosion at the south ends of the sows, at north sides of estuaries, like at Elsie Bay. Netarts Bay experienced these types of experiences in the previous El Nino winters. And then we have accumulation of sand in the far north. Well, it turns out it's even more complicated than that. So Dylan Anderson, who was a student of Peter Ruggiero doing his PhD work, started to sort of delve into trying to understand the relative contributions of these El Nino and La Nina events relative to normal cycles and what that means in terms of sediment transport. And so you can get at this by understanding and calculating the alongshore sediment transport flux and developing a time series of this information, doing numerical modeling. And so what he ends up finding is that since the 1980s, because of the prevalence of these El Ninos, which tend to result in greater northward movement, there's actually been a net northward drift of sediment during El Nino years. And that net northward drift is not being counteracted by an equally large enough southward drift. And so what that means is that places like Nesquin, along the north side of Tillamook Bay there by Twin Rocks, and other examples along the Oregon coast are experiencing greater erosion and more sediment being removed northward away from those areas, but that sand is not coming back. And that presents obviously a major problem as we shift towards ensuing winter seasons, which have the potential in any given year of producing extreme wave events like what I showed you earlier in that video clip. So another important aspect is obviously tides. And obviously on the Oregon coast, we have a semi-diurnal tidal cycle with 2 high tides, a lower and higher tide, and 2 low tides. In terms of water levels, our mean high water is around 8 feet. And the most extreme measured tide actually happened in 1969 and reached an elevation of about 12 feet. And so Jesse talked about, and Rhiannon, I think, talked about the role of king tides. And these king tides tend to occur around when we experience these 9 to 11 foot type tidal cycles as we're going into right now. And what's pertinent about those is that it's those high water levels combined with major storm events that really are resulting in the greatest degree of erosion along our coastline. And that's where this compounding flooding effect really starts to come into play. So in addition to the daily cycles, we also know from averaging these hourly measurements out through months and over multiple years, we can develop sort of a seasonal plot like this one. And so again, on the x-axis, we have time and months from summer all the way through to winter. On the y-axis, we have mean sea level in both metric and feet on the right-hand side. And so what we see is that during the summer months, as we are all probably familiar with, water levels tend to be depressed and closer to 0 in this case. And that's a function of the fact that we experience intense ocean upwelling that results in cold water coming to the surface, which basically depresses sea level. As you move to winter months, ocean upwelling breaks down and we shift to much, much warmer ocean temperatures. And through thermal expansion, our water levels actually increase by almost 3/4 of a foot. So the range here is what happens in a normal year, which is in the dashed black line. Then in El Nino years, these processes tend to be enhanced. In fact, we actually experience in 82, 83 and 97, 98, up to almost 2 feet of rise in sea level from summer to winter. So these are numbers that are very comparable to what's being forecasted as part of global climate change models for our region going out over the next 50 to 100 years. Except that we're experiencing these types of changes on a seasonal basis. And then, of course, every 10 years or more, 10 to 15 years, when we experience major El Nino events. And as we add sea level rise into this component, then we're compounding these problems going into the future. So what's happening with respect to sea level along our coastline? Well, it turns out that our coastline is characterized by a region of differential uplift, so a function of our proximity to the subduction zone. And so what you see is that north of about Astoria, our tectonics indicate the land is rising at about 3 millimeters per year. On the central Oregon coast, which is in this region here, our tectonics indicate a rise in the vertical land of about 1 millimeter per year. And then it reverses again on the south coast, increasing back to around 3 millimeters per year. So we have this differential uplift rate along our coastline. So we can take that information and we can take data from offshore satellite altimetry, and we can convert this to a relative sea level change rate. And this is work that Paul Komar and Peter Ruggiero and I did and published in 2011. And so we see this relative sea level curve for the Oregon coast. And what you find is that essentially on the central coast, from about Coos Bay all the way up to Tillamook Head, it's a region where sea level is rising faster than the land. So the coastline is slowly being transgressed or flooded. And then south of about Coos Bay, the rate of uplift is occurring faster than sea level rise. And so that part of the coast is emerging. And this is kind of captured graphically or figuratively in the images on the right there. So in Nehalem, for example, we experience flooding today. And that's a function of the fact that this area is slowly being submerged over time and sea level is rising. On the south coast, we have an area that's gradually emerging and sea level is falling, at least for now, because these processes are going to change in the future, and if not, are going to accelerate in other parts of the coast. And so this is work that actually stems from Sweet and others. That was published in 2022. So some of the earliest forecasts of global sea level rise was part of a National Research Council report that was published in 2012. When it first came out, the numbers were obviously not too bad, indicating rates of sea level rise on the order of about 1 to 2 feet. And then over the years, as NOAA has evaluated global climate models and then accounted for regional tectonics, accounted for glacial isostatic rebound and things like that, they've been able to refine these models as well and adjust the projections going out to the future. And what we're tending to see is that these projections are starting to get worse over time. And so the latest projections suggest that by around 2050, we can expect to experience anywhere from around 16 centimeters to as much as 30 centimeters. So around a foot of rise in sea level to as much as 2 to 3 feet of sea level by 2100. But again, the point is that when you factor in our seasonal cycle, the role of El Niños, we could be experiencing water level increases that will be approaching 4 to 5 feet by the end of the century. And obviously that has a big impact on coastal processes. So I touched on this right at the beginning of my presentation, that what we see on our coastline is really an analog of what's to come. And so here's examples of erosion in Gleneagles Beach, emergency riprap going in 2013, Nisquam Beach in 2008. Eventually that riprap structure collapsed and ocean waves started to erode into the building, more erosion in Rockaway Beach, large rates of erosion down in Nasika Beach, resulting in damage to building and properties. We're experiencing damage to our jetties and requiring, drastic remediation and extreme storms to try to mitigate those problems. And then, of course, flooding. And all of this is summarized in the right here, where we would be experiencing changes in coastal erosion, potentially more severe storm surge, changes in our tidal ranges over time, increased potential for flood risk, both run-up, overtopping, and inundation, potentially changes in sedimentation patterns, and then, of course, impact the structures. So all of this brings us back to, well, how do we actually start to utilize this information to begin to make, maps of the future? And in order to make maps, we need to have data. And we've got excellent data from tide gauges, giving us tidal information, from storms, from wave observations and things like that. But we also need, fundamental basic data about what our beaches look like at any given point in time. And so the schematic here in the mid photo shows a conceptual model of how beaches might respond. They respond from days to seasons to years, and then over multiple decadal cycles to climate change, sea level rise, tectonics. And our goal is to try to document the changes that are happening here so that we can actually utilize this information in making maps. And we do this by utilizing things like global positioning system that can be used to correct for errors as we operate on rover units, on jet skis. This is Peter Ruggiero and his team working offshore there using jet skis to collect bathymetry. We use GPS on backpacks to measure cross sections. We can mount it on a buggy to measure shorelines. We're now starting to utilize terrestrial laser scanning, basically a ground-based LiDAR system to map in detail changes at the back of the beach. We can utilize older technologies such as aerial photo interpretation. And then, of course, LiDAR, as I mentioned right at the very beginning, really underpins a lot of this work. And unfortunately, LiDAR is only collected roughly every 4 or 5 years. And so we miss a lot of critical information that could be filled in by utilizing these other types of approaches. So in terms of sediment budgets, I kind of touched on this earlier. We can differentiate between how beaches might respond over the short term to even long term. And so typically, if a beach is receiving sufficient sediment inputs and is not losing sediment, then it's probably sufficiently nourished and would be considered to be stable. So it'd be operating, fluctuating around some zero datum. In a beach system that is experiencing a lot of accumulation of sand, then there might be a situation where it's overnourished and that coastline is going to advance seaward. And the case in point is what's happened on the Clatsop Plains. And here's an example on the right here of one of our transect sites where we're showing the time trend from our seasonal surveys from early 2000 all the way up to the present. And we can see that this coastline has been actually accreting at about 10 feet per year over the last 2.5 decades. In contrast, at Twin Rocks in Tillamook County, we see a reverse. This is an area that's undernourished, where the long-term trend is actually towards erosion. It's eroding at about 3 to 4 feet per year. And we also see quite nicely in this image here the impacts of the 1997-98 El Nino, which caused very significant change in a single event, resulting in 20 meters of erosion, which is about 70 feet of erosion in a single event here. And so this type of information is critically important. And we can start to sort of utilize this information at different points along a cross-section on a beach. So the image at the bottom there is a cross-section. The landward side is characterized by high dune, and going to the left down towards into the intertidal zone. And so if you do measurements down closer to the tidal zone, the intertidal zone, we get a plot like this, which is in blue here. And what it shows is time on the y-axis and change on the x-axis. And you see that basically down closer to the tidal area, this is an area that's responding directly to seasonal changes in waves and tides. And we see a variation that can be on the order of 100 feet between summer and winter. As you go to the back of the beach, closer to the toe of the dune, we see much smoother responses. And up here, this is an area that's really being driven by storms. And so how we utilize this information is kind of critically important because they present two very different pictures about what a coastline might be doing. I would argue that using information from the back of the beach is actually much, much more meaningful. It's a much smoother picture and is easier to extrapolate more meaningful trends from than something that's happening down in the intertidal zone where there's a lot more variability going on. And this is one of the ongoing debates in the coastal literature in terms of how you utilize this type of information. But regardless, we can develop maps about coastal change. And so using our buggy where we measure shorelines in the bottom left there, all these little squiggles reflect about 60 measurements over 20 years. And you see lots of variation. That's almost 300 feet variation in the shoreline. So we can then process that data and develop a map for Tillamook County down close to the mean high water shoreline. And essentially, when you look at a map like this, so you've got Nesquin, Tierra del Mar, Sand Lake, Neatard Spit and Mid Photo, Bay Ocean Spit, Rockaway Spit, and then all the way up to Manzanita and the Halem Spit. The red and orange colors indicate erosion, and the blue colors or cooler colors indicate accretion. And so what you start to see from a map like this is that places like Neatard Spit is experiencing quite significant erosion. At the same breath, places like Rockaway Beach is also experiencing quite a bit of erosion. And we can see this in more detail in the two maps on the side there. But this is derived from looking at changes down near that sort of intertidal area. And so there's a lot more variation and the trends are much harder to decipher. So we can look at a a plot from our beach profile data where we're just focusing at the back of the beach here. And the upper plot is for the central coast down in the Newport area, running from Yaharts in dark blue here all the way up to Beverly Beach. And so this is an area that's characterized by bluffs as well as sandy beaches like LC Spit, and then a little bit of around Agate Beach, around South Beach by the mouth to Yaquina Bay. And in the bottom image, we can see similar plots for Tillamook County and Clatsop counties. And we see lots of interesting variations. We see effects of, like in the Rockaway area, we're seeing erosion down by Cape Meares, but very significant accretion, greater than 10 feet happening adjacent to the mouth of Tillamook Bay. On the north side by Twin Rocks there, very dramatic erosion, minus 10 feet down here, all the way up to accretion up by Nadonna Beach, and then accretion along the Halem Spit. And so what we're seeing from these types of data is when you plot it over multiple cycles, is we're seeing a reorientation in our shorelines, where the southern ends of these pocket beach littoral cells are tending to erode more, and accretion's happening at the north ends of cells. We can develop similar erosion data from other areas along the coast. So this is the Coos County area. And here we only have LIDAR data. We only have 6 data points collected from LIDAR from 1997 all the way up to 2016. And this is using the back of the beach in these examples. And again, you can see in terms of erosion rates, which is on the x-axis, metric on the bottom, feet on the top, and then northing going from New River all the way up to Cape Arago at the north end on the left plot there. You can see a lot of squiggliness happening essentially south of Bandon on the barrier beaches that's associated with the New River mouth, ranging from both extreme erosion to extreme accretion. And then as you go north of Bandon, things start to settle down and become much quieter, especially once you get up into the bluff back areas where the erosion rates are clearly less than a foot or two over the long term. And then the image on the side is for the North Coos Spit again, where we see erosion rates that are much more uniform, dominating the entire section of the North Spit there, that are somewhere, on the order of 2 to 3 feet on average. So this type of information becomes very critical. And as we get onto the coastal bluffs, we have some challenges. And so the traditional approach has been to utilize aerial photographs, where you measure a distance from the house to the top of the bluff. We can utilize LIDAR in some cases, or we can actually use GPS and try and walk down a cliff, which of course is very dangerous and probably a bit of a dumb thing to do because you're liable to fall over, break a leg or something like that, or get hit on the head with a rock. So there's newer technology such as laser scanning, where we can set up an instrument at the base of the cliff and scan at very high resolution what's happening on these bluffs here. And this is something we've started doing on the central Oregon coast in the Newport area at Beverly Beach. So here's an example in the upper left there is a scan in October of last year, a follow-up scan in April of this year. This is Astoria Formation rock. You can differentiate different geologic units within this rock. And you can see in the bottom image, which is basically a difference of the two data sets, you can see that the bulk of this cliff here didn't change very much. But on the right, in red colors, are areas indicating very extreme erosion, and in green to blue areas of accumulation. So utilizing these data, we can start to begin to build up a picture of what's happening on the coastal bluffs that provide us with much more detailed information than relying on single transects or even extracting trends from the base of the cliff or even from the top of the cliff. So what does it all mean in terms of hazard mapping? Well, we can take all this information and we can begin to develop maps using a variety of different approaches. And so this is for duneback beaches, we use a 4-dune erosion model. And basically the primary inputs into this type of model is information about the slope of the beach, information about the elevation at the back of the beach, what we call the beach dune juncture. And then we calculate the wave run-up and superimpose it on the tide. And then we can start to play games by incorporating sea level rise and other types of effects. And so the basic equation that we use for calculating this change is in the bottom of this conceptual model. So in order to apply this and develop maps, we have to develop scenarios. And so we did this for all of the central to northern Oregon coast. So we've actually developed erosion maps in 2001, and then there were updates done in Lincoln County in 2004 and 2007. And we've also completed similar mapping down in the Gold Beach area. But we use deterministic maps deterministic scenarios that are based around extreme wave events, extreme tides, and these are sort of summarized at the bottom there. So for example, a high hazard zone is associated with a 50-year storm wave happening with on mean high water with a 3-foot storm surge, whereas a medium scenario is incorporating a 100-year storm wave, and then a low scenario incorporates coast-seismic lowering. So that's where we can actually account for lowering of the coast due to a Cascadia earthquake. And then we project these erosion zones out on the landscape using LiDAR, like I showed before. So here's an example for Tillamook County. And so keep in mind that this mapping was done in 2001, and the aerial photos that you see here are actually taken in 2002. And so when the mapping was first done, we used LiDAR from 1998. And basically the western or seaward edge of that red zone was where the beach was, the toe of the beach dune junction was in 1998. Well, you can see in this example, this is the RV park at Shore, I'm struggling to remember the name of it, by Twin Rocks, is now, you can see in 2022, there's been very significant erosion at this particular location, getting close to almost 70, 80 feet at this particular site, and even now starting to extend to our moderate zone. In contrast, up at Manzanita, we see very significant accumulation of sand that's happened since then. And so these maps are telling us that maybe we need to start to rethink about how these were made the first time around, and maybe we should be updating them. Well, in 2012, we actually did try to update these maps, and we took a more sophisticated approach by using about 150 extreme storms, and we did a probabilistic analysis where we start fitting curves to all those calculated run-up elevations and tides and combinations. And then we added sea level rise based on updated estimates from the NRC report in 2012 and projected those out into the future. And so we start to see the impacts of sea level in a community like Twin Rocks here. It starts to look a little more grim as we go to much more extreme scenarios at around 2100. And then if we incorporate a lowering of the coast, we see the greatest potential for erosion and incursion. We can do the same thing, but using a different model for coastal bluffs, which is really based on erosion rate data. And so these data that's shown in this table up on the left there reflect change rates defined using a house to bluff top measurement, which is very crude with high errors associated with it, but it was the best available information we had at the time. And the point here is that with all the new data that's starting to become available, we can certainly do a much, much better job of defining these erosion rates now going into the future. But anyway, at the time, this is what we had to work with. And so we use these erosion rates, and based on different geologic units, we make projections out into the future from the bluff top and erode the coastline to reflect that. So again, we've got a high hazard zone, which is expected erosion over a 50-year time frame, up to an extreme erosion up over 100 years. We also incorporate landslides and assign block failures and things like that to result in a much more complex product. And so this has been done for, as I said, all of Lincoln, Tillamook, and Clatsop County. The data are used by local planning departments through a combination of ways for triggering site-specific erosion hazard assessments that geoconsultants may be contracted with to come in to evaluate an erosion problem that may be happening in a house and things like that. And it's used for pre-planning future development as well. But the main point to note is that we do have these maps, and we should be starting to think about the effects of climate change out of the future. So where can you find a lot of this information? Well, there's a variety of sources. You can go to the DOGAMI website, you can do a search by publication, and you can find information by counties or by subject in terms of whether it's erosion or hazard maps and things like that. If you want to see information about what's happening at specific points, these are all our beach monitoring sites. Excuse me, on the central to north coast, we have similar sites on the south coast. We don't get to them all the time. The ones that we do measure more frequently happening in Tillamook and Clatsop County, but you can see change rates similar to what I showed earlier, and you can contact me directly if you are interested in specific types of information. If you want to look at hazard maps, you can go onto our HazView site and you can overlay the erosion hazard maps and see what those look like in a map like this. So lastly, I want to finish up with what about expectations in a subduction earthquake? And so the best analogy for this is what happened in Tohoku, Japan in 2011. So these are two examples of two different sites. One at Nanakita River mouth, published by Tanaka and others in 2012. You can get a sense of the scale of the map there. In the upper left corner, that's 200 meters, which is about 600, almost 700, 650 feet. And you can see just prior to 2011 tsunami event, you have a barrier spit, a broad beach system. Following the event, that spit is now gone. We've seen, you can see remnants of the spit, all that sand's been carried in. It's impacted the main river channel. And then over time, quite rapidly, the barrier spit there starts to rebuild. But on the north side, we're seeing very extensive erosion taking place. And that erosion continues to accelerate northward over time at this particular location. And the river mouth, in this case, switches to the south by September of 2011. A similar plot here on the right shows something very similar. This is pre and post tsunami impacts. You can see the original shoreline in black in the bottom image there, and the coastline is now starting to erode. So clearly this is a consideration as we develop maps for the future, when thinking about both climate change, but also the earthquake that's will happen at some point in the future. So this is an area of focus by a PhD student, Carly Ringer, working with Megan Wengrove, myself and Aaron Peck and various other folks. This is a Sea Grant funded study, and the goal here is to understand the role of tsunamis as they erode sandy beaches and erode foredunes. And this is very much in its early days. And the preliminary results that came out of this study, this is comparing our M1 or medium scenario. So it's not the most extreme one used in our evacuation maps, but it's most closely analogous to the 1700 event, I guess. And so the preliminary results in her modeling work indicates that in some areas, when you include erosion, you start to see greater inundation, and in other areas, it doesn't work that way. So it's complex, and but this is an area of ongoing interest and focus. On the far right there is the movement of sediment that would occur as a result of this type of tsunami event through the modeling. And so we see masses of sediment being moved into Neatouts Bay, but also large volumes of sand being moved offshore in a variety of different areas. Where this really comes into play is that her work is also going to evaluate the effects of dune grading. And that's particularly important because while these large dunes may not result in greater inundation in a cascading event, they do provide significant protection from distant tsunami events, such as an Alaskan tsunami event. And so an area of focus has been directed at understanding the role of dune grading on the Oregon coast and the potential implications for increasing distant tsunami hazards in certain communities. And so this is an area of focus that Carly's going to be delving into as we go into the future. And lastly, I just wanted to acknowledge my colleagues, Laura Gable and Fletcher O'Brien, who have been instrumental in helping collect a lot of the data that we work with in terms of our surveys, but also a lot of the data processing that goes on behind the scenes. And I'm happy to stop there.
Thank you so much for that. That was amazing. And we'll open it up to questions now. So if you have a question, feel free to either use the Q&A box or you can type it into the chat. And if you would prefer to ask your question directly, go ahead and raise your hand and we can take you off mute. And just a reminder, there will be a recording of this. It will be sent out to you over email in the next few days, and it will also be posted on both the Surfrider and the Oregon Shores YouTube channels. There's a question in the chat here from Julie. She's wondering, how can regular citizens / residents contribute to getting you more data?
Yeah, this is a great question, and so there's a couple of ways that this could be handled. One approach that is being used and implemented around the world is what's called CoastSnap. And the idea behind CoastSnap is you establish these monuments at various key areas, key beaches along a coastline. And essentially, it has a frame attached to the monument or a post, and you insert your phone into that frame and it takes a photo. And then you upload the photo and it goes to the CoastSnap site, it's processed, they run some algorithms on it, and they can extrapolate information about the shoreline at the time the photo was taken. And you can then start to build up a picture of coastal change. And so that's something that was developed actually in Australia, but it's now really being adopted worldwide. There are 2 sites that have been established up on the Washington coast. And this is something I've been sort of suggesting on a number of occasions to folks to consider, particularly in Oregon Sea Grant, is establishing sites like this, a few sites like this on the Oregon coast where we know people frequent, and we could begin to develop really good time series information about what's happening at those locations. And I think that has great value from the standpoint of being able to extrapolate meaningful information in a systematic way, but it also allows you to capture cool photos of the impacts of, say, king tides and storms, providing it's all done in a very safe manner. So I think that's something that could be explored and should be explored going forward. And I've certainly had conversations with Peter Ruggiero at Oregon State and a few other people about this.
Great. I think that is also, you can submit your photos on the King Tides Project website. So if you're looking for a way to contribute, I think that's a really good way as well. There's another question here from Pat. They want to thank the wonderful scientists that are doing this research, but are wondering if there's a way to receive this information in a language that is more understandable to non-scientists.
Yep, that's always a challenge, and I'm terrible at trying to constrain a lot of information into a simple format. I mean, I think the best approach is there is a really excellent book that was written by my former mentor, Paul Komar. I encourage everyone to read it. It's about the Pacific Northwest coastline. I can pop the title of the report in the chat in a few minutes. But it's a beautifully written book about the history of the Oregon coast, the role of physical processes in affecting the coast. There's some great stories about areas like Cape Meares and the breaching of Bay Ocean Spit, the idea of establishing an natatorium out there, things like that. And it's really written for the layperson, and I highly recommend everyone who is interested in basic coastal geology and geomorphology to read it. It really is outstanding.
Jonathan, this is Jessie. Can you please repeat the name of that book so that we can write it into the chat and the author, or maybe you could put it in there yourself?
Yep, I'm just pulling it up. It's I'm having a brain freeze.
That's okay. We'll help you. I think Rhiannon's looking too.
Is it the Pacific Northwest one?
Yep, that's the one.
Yeah, I'll put it in there.
Oh, it's the one that was published by Oregon Shore, like republished by Oregon Shores, I think. Great. Okay.
Yep, it's the Pacific Northwest coast.
By Stuart Schultz.
Living by the shores, living with the shores of Oregon.
Is that the one by Stuart Schultz? Is that right?
Here, and you can actually buy it on Amazon, of course. So the title's there.
Thank you. Great.
And I really do highly recommend anyone who wants to learn about the Oregon coast. And a lot of the things that I've talked about here are discussed beautifully in that book.
And then Jill also had a great suggestion of going on the DOGAMI website and looking at the maps. She says that's an easy way to see the science in action. And I think another good option would be, and Jessie kind of alluded to this in the chat, are there any good animations or videos that you know of that kind of explain this?
I'm sorry, are there any good animations?
Yeah, something easily digestible, maybe.
You know, that's a great question. It's not something I've actively gone looking for, but it's certainly something that I could, do a little bit of sleuthing around. I mean, there are definitely various coastal research centers around the US environment, the US coastline, and you could certainly just do a quick Google and you can find some information about those sites. Oregon Sea Grant has some great information. I know DLCD through the Coastal Management Program has some great information and sort of various schematics and things like that. So definitely, utilize those types of data sets that are out there. But I don't have anything specific that I can point to immediately. Rhiannon, I know I saw you had your hand up.
Oh yeah, I was just going to point people to Oregon Sea Grant as well. And we do have on the Oregon Coastal Atlas from DLCD. We have a lot of good resources, and I will put that in the chat as well. Or Jessie, if I'll send it to you and you can put it in there, please.
And then I think Susanna, looks like Gladwin, asked the question about, did you factor in post-Cascadia quake subsidence? And yes, the short answer is for the erosion mapping that we did on the Oregon coast, we did incorporate coast-seismic response, and that's factored into our low hazard zone. So it's the most conservative, it's the broadest erosion hazard zone. And one could flip that and use that as also as an indicator of sea level rise, because it's basically equivalent to a rise in sea level of about 3 feet. So it works both ways. Someone asked a question about when homes are built too close to the shore and are destroyed, who pays for the cleanup? That's a question probably to Oregon State Parks and Rhiannon. I believe the homeowner is responsible.
Yeah, that cost would go to the homeowners if it's on their property, and if it's on the shoreline, if it's within the OPRD shoreline for Parks and Recs, then it's up to the property owner to clean that up.
And luckily, I'm not aware of too many situations. In fact, I'm not aware of any situation where a home has been eroded and fallen onto the public beach per se. I am aware of a number of situations where homes have been lifted off their foundation and moved inland away from the eroding coast. There are examples of that in Falcon Cove up in Clatsop County. There's examples of that near Glen Eden Beach. but they're relatively few and far between for sure.
We have some really good links in the chat, so if you are interested in those other resources, take a look in there. Well, we have a few more minutes for questions, but if there are no more, could wrap it up. Oh, something's coming through the chat.
Yeah, I think to Kristen's comments there, I mean, the modeling and mapping work that we do is very simple. It's very two-dimensional, and part of the reason for that is that in order to implement more complex modeling, and there are numerical models that could be scaled up to account for broad shoreline changes, but those types of models require extensive data input and a lot of calibration type work, and so the cost to actually do that type of work is quite prohibitive right now. And in time, I mean, as the science and physics is resolved better, certainly those types of models will become more easily used, and the more data we can get and input into those models, the better they're going to be. I mean, that's the thing about it. They take a lot of tweaking to start to pull out meaningful type results. But I think it's very clear just from when you compare the changes from the original mapping work that we did in 2001 and overlaid on contemporary photos, you can see the non-linear type responses that are happening along our coastlines, and that's the challenge. And so if we use these simple types of approaches, which are definitely very effective, then it just means that we need to be updating them on a more frequent basis, updating in the sense that maybe rather than every 20 years, it's been 23 years since we did it, maybe we should be looking at 10 to 15 years to update map products like this, because of course, the coast is changing all the time.
Great. Well, I will just plug again, our last webinar of the year will be December 4th with Peter Ruggiero at 6 o'clock, and you can find that registration link at the bit.ly link that was shared earlier, or I can share it again. And we will be able to send out all of these links that have been shared, all of these different resources in a follow-up email for that question about how to save the chat.
Yeah, I just put that into the chat that when we send that follow-up email, we'll include everything in there for you all.
And if you'd like to get in touch with myself, with Jessie, or with Rhiannon, you can find our information on this slide.
Yes, and please don't hesitate to reach out to me directly through the Oregon Department of Geology. I'm happy to answer questions that way as well.
Great. Well, thank you all so much for joining us tonight. I hope you enjoyed it, and I hope to see you next month.
Thank you.
Thanks, everyone. Bye.
Thank you. Bye-bye.
Thanks a lot, Jonathan.
We still have...
Everybody, take care. Kai, I'll talk to you soon. Trying to figure out
Bye.
how to end this thing.
Yeah, I think that if we just leave, it will end it all.
It will end. Yeah.
Okay.
Okay.
Bye.
Take care. Bye.